everyone, welcome to my YouTube channel Erudispace. I am Dr. Mohanty, and today we will discuss about the performance parameter of internal combustion engine. So here we do have 5 efficiencies and then other related performance parameters. Once you understand all these things, your concept about the different performance parameters will be clear, and you will be in a position to actually find out the performance of the internal combustion engines. So you do have 5 efficiencies. They are your indicated thermal efficiency, your direct thermal efficiency, your mechanical efficiency, your volumetric efficiency, your relative efficiency, and apart from that you have other terms. So first we will discuss the first 3 efficiencies, that is the indicated thermal efficiency, the direct thermal efficiency and the mechanical efficiency. These efficiencies are never discussed in isolation. So it is always prudent to first understand how the energy conversion is actually taking place. So first, you do have the power in fuel supplied. Some of the authors, they represent this as the energy in fuel supplied also. And after that, you have power that is developed inside the engine cylinder. And then you have the power that is available at the crankshaft. This one is maximum, this will be less than that, and this one will be less than that. Why this is happening? What is actually the power in fuel supplied? The power in fuel supplied is the power that can be obtained due to complete combustion of the fuel, and we calculate this by considering the mass flow rate of fuel multiplied by the calorific value of the fuel. We will discuss in detail about the calorific value, both higher calorific value and lower calorific value in this lecture itself. For the timing, remember that the power in fuel supplied is the product of mass flow rate of fuel multiplied by the calorific value. Then the power that is developed inside the engine cylinder is found to be less than the power in fuel supplied, because some of the energy flows through the exhaust gases, some is transferred through the coolant, and there are pumping losses also. That means some of the power is utilized in forcing the charge into the engine cylinder and forcing the exhaust gases out of the engine cylinder. So for that reason, the power that is developed inside the engine cylinder is found to be less than the power in fuel supplied. Then the last one is power that is available at the crankshaft. The power that is available at the crankshaft is again lower than the power that is developed inside the engine cylinder, because you are having the moving components. You know that you do have a piston, connecting rod, crank mechanism. As a result, the power that is developed inside the engine cylinder is converted into your mechanical work. So as your moving components, frictional losses will be there. As a result, this one will be the lowest. This one is maximum, this will be less than that, and this one will be further less than this. Now, once you understand this, it will be very easy for all of you to understand the first 3 efficiencies. First we will discuss the indicated thermal efficiency, followed by direct thermal efficiency, followed by mechanical efficiency. So indicated thermal efficiency is the ratio between the power that is developed inside the engine cylinder to the power in fuel supplied. So this one is the power that is developed inside the engine cylinder divided by the power in fuel supplied. Some of the authors, they do use the term energy in fuel supplied, but they represent the same thing. This is your indicated thermal efficiency. Next one is your brake thermal efficiency. So what is brake thermal efficiency? The brake thermal efficiency is actually the ratio between the power that is available at the crankshaft to the power in fuel supplied. So this one will be substituted. Here you write the power that is available in the crankshaft. This one is your brake thermal efficiency. Now, the last one is your mechanical efficiency. Mechanical efficiency is in fact the ratio between the power that is available in the crankshaft to the power that is developed inside the engine cylinder. So, you can represent the mechanical efficiency as power available at the crankshaft divided by the power that is developed inside the engine cylinder. And this mechanical efficiency may also be represented as the ratio of the indicated thermal, the ratio of the brake thermal efficiency to the indicated thermal efficiency. These three efficiencies are very, very important. Then the next one is the volumetric efficiency. All of us know that the amount of airflow mixture drawn into the engine cylinder is found to be less than the displacement volume. Already I have discussed in detail about volumetric efficiency of an internal combustion engine in a separate lecture. If you have any doubt about volumetric efficiency, you can refer to that particular lecture. But I would like to inform you that the contributing factors for which the volumetric efficiency is less than 100% is due to the fact that some amount of gases is trapped in the clearance volume that expands, which actually resists the flow of airflow mixture into the engine cylinder during the first part of the suction stroke. The residual gases present as well as the high temperature of the cylinder also affects the volumetric efficiency, as it is used to expand the gas that is coming to the system. Then you have other factors like design of the intake and exhaust manifold, as well as the valve opening and closing. That I have already discussed. Now, what is actually the volumetric efficiency? That is the actual amount of airflow mixture drawn into the system divided by the volumetric displacement. Now, you can define the volumetric efficiency in this way. This is mass of air divided by the density of air. That represents the actual volume of the working substance drawn into the system divided by volumetric displacement multiplied by N by 2, and this is specific to a 4-stroke cycle engine. Then coming to the last of the efficiencies, what we call your the relative efficiency. The relative efficiency is actually the ratio between the thermal efficiency and your air standard efficiency. All of us know that why the concept of air standard cycle is perceived, because internal combustion engine in true sense doesn't execute a cycle, because the combustion itself brings about some chemical changes which makes it completely irreversible. So for that reason, air standard cycle is perceived, and the air standard cycle is supposed to undergo the same processes as undergone by the actual working substances in actual internal combustion engine. Now, although it is not feasible to run an internal combustion engine using this, we can compare the performance of any other engine with that of the air standard cycle, and the relative efficiency is actually the ratio between the actual thermal efficiency divided by the air standard efficiency. Next, what we'll discuss is about the mean effective pressure. This mean effective pressure is actually calculated from the indicator diagram, and mean effective pressure is the average pressure which, if acts during the expansion stroke, will have the same power output as obtained under actual working condition. But pressure never remains constant during the expansion stroke, but this is something that will give you the average value of the pressure. But mean effective pressure doesn't have any physical significance. Let me draw the PV diagram of Otto cycle. Otto cycle consists of 4 thermodynamic processes. They are your isentropic compression, followed by constant volume heat addition, followed by isentropic expansion, and followed by constant volume heat rejection. Now, how we calculate the mean effective pressure? We calculate the area coming under the PV diagram, and then we actually divide it by the swept volume. This is actually your swept volume, and we divide this area by the swept volume, and this actually gives us the mean effective pressure, that is EM. And how we calculate the indicated power? Already I have told you that indicated thermal efficiency is the ratio between the indicated power and the power in fuel supplied. Power in fuel supplied can be easily calculated by multiplying the calorific value with the mass flow rate of fuel. But how actually this indicated power is calculated? Indicated power IP is equal to mean effective pressure multiplied by length of the stroke multiplied by area per section of the piston, then N is number of working stroke divided by, multiplied by letter K divided by 60 into 1000, and this much kilowatt, where mean effective pressure is represented in Newton per meter square, length of the stroke in meter, the area of cross section of the piston in meter square, N is actually the number of working strokes per cycle, and this N is equal to capital N for 2-stroke engines, and N is equal to capital N by 2 for 4-stroke engines, because you know that in a two-stroke cycle, it is equal to the number of revolutions, because in two-stroke or a single revolution you are having one working stroke, but in that case it is n by 2. So this is about the value of n, and we are dividing it by 1000 so that we can represent this in kilowatt. K actually represents the number of cylinders, because we may use more than one number of cylinders. As far as this term is concerned, this actually represents the mean piston speed. So what is mean piston speed? Mean piston speed is 2Ln. All of us know that the piston undergoes reciprocating motion inside the engine cylinder, and in a single revolution it undergoes two reciprocation. So if n is the RPM, then the mean piston speed is 2L into n. This one actually represents the specific power output. So what is specific power output? Specific power output is the ratio between the power that is developed divided by the area of the piston. It doesn't take into consideration the cylinder volume. Specific power output is actually the ratio between the power that is developed divided by mean piston area. This one is your specific fuel consumption. So specific fuel consumption may be brake specific fuel consumption, it may be indicated specific fuel consumption. Brake specific fuel consumption is on basis of brake power, and indicated specific fuel consumption is on basis of indicated power. So what is actually specific fuel consumption? Specific fuel consumption is the fuel consumed to develop unit power. So that is the ratio between the mass flow rate of fuel, that is the fuel flow rate for unit time, divided by the power. So BSFC, brake specific fuel consumption, is the ratio between the fuel flow rate, that is the mass flow rate of fuel in kg per unit time, divided by the brake power. Similarly, the indicated specific fuel consumption is the ratio between the fuel flow rate divided by indicated power. So you should not get confused between BSFC and ISFC. Next one is the fuel air ratio or your air fuel ratio. Either it is represented as fuel air ratio or air fuel ratio. So that is also very important performance parameter, because that affects the performance of the internal combustion engine. So understand this, you should also understand what we mean by stoichiometric ratio or chemically correct ratio. The chemically correct ratio is the fuel air ratio where the air supplied is just sufficient for complete combustion of the fuel, and the stoichiometric ratio usually is in the range of 15:1. That means 15 volumes of air and 1 volume of fuel. Now, when you have the exact value, then you can say that it is equal to the stoichiometric ratio, and it is stoichiometric ratio itself. If you are providing more amount of fuel, that becomes a rich mixture, and if you are providing a less amount of fuel, that is what is your lean mixture. That means the air content is more. So that you need to understand as far as the fuel air ratio or air fuel ratio is concerned. It has a very wide range, maybe from the range of 12:1 to maybe 60:1. There is a wide range of air fuel ratio that is maintained in internal combustion engines depending upon the requirement. The last one is your calorific value or your CV. I have discussed that how actually we calculate the power in fuel supplied in details while explaining the indicator thermal efficiency, brake thermal efficiency as well as mechanical efficiency. But what is the calorific value? Calorific value is actually the amount of heat that can be developed due to complete combustion of unit mass of that particular fuel. But we do have two calorific values. They are your higher calorific value and lower calorific value. So what is higher calorific value, what is lower calorific value? So whenever actually combustion of fuel takes place, certain amount of water vapor is formed, and if that water vapor is brought to around 25 degrees Celsius, then some more amount of heat energy is developed. When that is done, that represents your higher calorific value. When that is not done, then that becomes your lower calorific value. So I sincerely believe that after this lecture, your concept about the different performance parameter, which includes the 5 important efficiencies, the mean effective pressure, the mean piston speed, the specific power output, the specific fuel consumption, your fuel air ratio or air fuel ratio, as well as the calorific value, will be very, very clear. And you will able to work out numericals of any level of difficulty related to these performance parameters. Thank you very much for watching this video. If you have any doubt about this particular lecture, you may put questions so that I will try to answer. Thank you again for your cooperation. Hope to see you soon for another lecture in my YouTube channel, Erudispace.